In this video, we'll look at some general properties of ionic compounds. To begin with, they're crystalline. And we kind of looked at some videos early on at the beginning of this unit that showed what a crystal was. It's basically just a substance that has a very organized structure. And so maybe we could just make note of that. In general, crystals are substances with an organized structure. Ionic crystals will have a very organized pattern of oppositely charged ions, and they'll arrange themselves so that we maximize attraction and minimize repulsion. So I don't want two negative ions really close to each other. They're going to repel. And so we try to organize them in different shapes and structures so that we can maximize attraction and minimize repulsion. And eventually that gives us crystals with different shapes. So they kind of show this rutile and fluorite, that the fluorite is a little more cubic, and the rutile has kind of these needle-like crystals. And a lot of that just comes from the way that the ions organize themselves. But in general, ionics are very crystalline, very organized. They can conduct electricity when in solution. Okay, so solubility means the ability to dissolve, and many ionic compounds do dissolve in water. And when they do, when an ionic compound dissolves, the ions break away from the crystal and become surrounded by water molecules. This is something that we'll talk about a lot more later on, even into second semester. But they kind of show this example and this little particle model down below that if I had I don't know, this looks like sodium chloride. If I had a crystal of sodium chloride, now obviously this isn't exactly what it would look like, but let's say it's, oppositely charged ions, and they're in a very organized crystal structure. Okay, so it would be like opposite ions, positive, negative, all throughout the crystal. Positive, negative, positive, negative, positive, negative. And so this could be any, general crystal. It could be sodium chloride, where the sodium ions are positive and the chlorine ions are negative, or any positive, negative ion for that matter. And so what happens then is that when you put this in water, the water molecules are attracted to the ions in the crystal. And so the little water molecules will kind of surround each ion, and eventually they'll try to remove the ions from the crystal. So they'll separate the ions from the crystal, like so. And then eventually you have something that looks like this, where here the negative ions are the chlorine. So by these green particles, I'm just going to put like a little negative charge in there. Negative chlorines. And then the positive sodium ions look like they're orange. Positive, positive, positive. And so that's what it looks like when an ionic substance dissolves in water. So the little charged ions separate from the original solid, and then they're just swimming around in the water. And so then it obviously has properties of a liquid in that there's no structure anymore. There's no rigid, solid structure. The ions are now free to move and flow and can intermingle with all the water molecules. Now this would be what we call a physical change, in that if I just evaporate the water, then the ions will suck back together in the original solid crystal. But as long as there's still water present, the little ions kind of swim around and intermingle with the water molecules. And so a lot of ionic compounds are water soluble in that they're very attracted to water molecules. And then that kind of helps to separate each little ion from the crystal. All right, cool. So then what you end up with is a bunch of moving charged ions. And guess what? Moving charges will conduct electricity. So solubility was the ability to dissolve in water and form separate little ions. Conductivity requires moving charges. Requires moving charged particles. Or in this case, ions. So as long as these ions are free to move and flow, we can conduct an electric current. And so we'll try this in a lab where we'll take a solution of something like sodium chloride, and you can put electrodes in there or a conductivity tester or a battery, and you should be able to conduct an electric current. Crazy, huh? I mean, that's why they say you shouldn't drop your hairdryer in the bathtub. Tap water is not pure. It contains charged ions. There's magnesium ions and chlorine ions and fluorine ions and zinc ions. There's all kinds of charged ions coming out of the tap. And so tap water just naturally conducts electricity. But the key is we have to have moving charges. Moving charges. Okay, so that's why in solution the ionics will conduct electricity, because the charges can move. Sometimes you can melt ionic compounds, and when molten, they can also have ions that are mobile, that can move, and you can conduct an electric current. So I'm going to just make a note. Yes to conductivity. Yes to conductivity is when we're in solution or molten. So the ionic compound must be in solution or molten. Solution, or I'll say liquid. And the difference is that in solution, it looks like this, where the ionic solid was dissolved in water, and the ions separated and they're free to move. Molten, or liquid, would mean that I would have to heat the original solid. And if I can heat some ionic compounds enough, they will melt, and then those ions can just move, but there's no water molecules present. You would just be able to kind of soften the crystal structure a little bit. And as long as those ions can move, we can conduct electricity. But here's going to be a no to conductivity. When the ionic compound is solid. Ionic solids will not conduct electricity. So if I just take a pile of salt and put a conductivity tester in it, no luck. You will not conduct electricity in the solid phase, because in the solid phase, the ions cannot move. We need moving charges to conduct electricity. So we can have moving charges when either the ionic substance is dissolved in water, and then the little ions separate from the crystal, they can move around, or if we melt the ionic solid, then the ions can move and flow a little bit, but not in the solid phase. In the solid phase, you've got a very rigid crystalline structure, and it would be like this. Those ions are not moving. Not when they're so strongly attracted to each other. I mean, every little positive ion is totally covered with negative ions, and you've got really, really strong attractive forces. And so those ions are not going anywhere. They are not moving in the solid phase. Cool. And then one other thing that we should mention is that typically ionics do have really high melting points. So high melting points. They're typically so high because of the strong attraction. Strong attraction of oppositely charged ions. Opposite charged ions. I mean, think about like that little picture that we drew with the ionic solid, where there's positive, negative, negative, positive, negative, tons of charged ions, and they're packed so tight together that there's just a lot of attraction. And ionics often have really, really high melting points. So for example, like, we'll try it, but you can't melt salt in our lab, and like not with a Bunsen burner. There are some ionic salts that we can melt that just have a little bit lower melting points, but not something like sodium chloride or like not magnesium oxide melting at almost 3,000 degrees Celsius. Yeah, that's not going to happen in our lab. Ionics in general have really, really high melting points because of the strong attraction of the oppositely charged ions. Now, this is what's kind of interesting about the example that they give us here. They tell us up here that the sodium chloride melts at about 800 degrees and magnesium oxide melts almost 3,000 degrees. That's insane. Now, those are both considered high melting points. But what if somebody asked you, why is the melting point of magnesium oxide greater than the melting point of sodium chloride? And so again, like if we're melting, it's endothermic, we're adding energy, we're trying to separate the particles, so instead of being tightly packed in a solid, they can flow and move around in the liquid phase. So what about the structure of magnesium oxide makes the melting point so high? And guess what? It has to do with our buddy Coulomb's law, right? So Coulomb's law looks at two factors. Number one, magnitude of charge. Okay, well, let's think about the charge of sodium, chlorine, magnesium, and oxygen. Okay, sodium has one valence electron, and it's likely just to lose that one valence electron, right? If I lose an electron, the charge is +1. Chlorine has 7 valence electrons, and we'd like to just gain one more. If I gain one more, then I have a full shell and a -1 charge. Okay, that makes sense, right? So now if I think about magnesium oxide, magnesium and oxygen. Magnesium has 2 valence electrons, and we'd probably lose both of them, right? Charge of +2. And then oxygen has 6 valence electrons, so now we're probably going to just gain 2, right? So I gain 2, -2. So with Coulomb's law, we said the number one thing that affects the strength between oppositely charged particles is the magnitude of the charge. Well, check this out right here. Winner, right? Magnesium and oxygen have higher charges. But now the other factor we look at is the distance between the ions. We want small ions that can pack real tightly and be real close to each other. Well, here we're going to like double tip the hat to magnesium and oxygen. Because look at sodium and magnesium on your periodic table. They're right next to each other going across the row. So they both have electrons in the 3rd energy level, but magnesium has an extra proton and an extra electron for a stronger attraction, right? So magnesium should be smaller than sodium, and oxygen is definitely smaller than chlorine. Oxygen only has electrons in 2 energy levels, but chlorine's going to be looking to fill the 3rd. So not only do you have higher charges, but you've also got smaller ions that can pack real tight and show stronger attractions. And so if I've got stronger Coulombic attractions, It's going to take more energy to separate the ions. Now, by the time you get to this question 8 here, then they say, what if you have a couple unknown solids and you want to use some of these properties to determine whether or not they're ionic? I would just go back to some of these examples. Test it in the lab. Look at the melting point. Try melting it. Does it have a really high melting point? Then it's probably ionic. Look at solubility. Try putting a little bit in some water. Does it dissolve? If it dissolves, then it's probably ionic. Or check then the conductivity when you get it in solution. If it conducts, you've probably got an ionic solid. Now you maybe could look at the crystalline structure under a microscope. You could look at little sodium chloride crystals under a microscope and tell that they're kind of cubic, they're all very organized, whereas something like sugar might just have random shapes and sizes of particles. But any of those properties, whoopsies, there we go, could be used to answer question 8, determining whether or not your solid is ionic.